Alright, this video is Calculus 30, Chapter 2 review. Okay, this is what it is, review video. And we started off Chapter 2 by talking about the derivative. What actually is a derivative? We had not mentioned what a derivative was up until Chapter 2, Section 1. The derivative is the name given to the instantaneous rate of change for two variables, which is the slope of the tangent line to a curve at a specific point. So everything that we did in Chapter 1, finding instantaneous rate of change, we are just now calling it a derivative. So that's what the derivative is, everything that we've already done in Chapter 1, like down here, right? This is what you remember from Chapter 1. So we've been using limits to calculate these values. In Chapter 2, what we did was we learned new shortcuts for the process of differentiation, which is what finding a derivative actually is called. So that was the first section. We just kind of talked about how to connect what we've been doing in Chapter 1 with the new verbiage or the new terminology for Chapter 2. We talked about that a function is differentiable at a if f prime of a, and this is the new notation here for the derivative of the function with respect to a, f prime of a. It's differentiable if there exists a derivative for every point on the interval. Okay, so if a function has no gaps or no spaces, no jumps, if it is continuous on the entire domain, then we say that it is differentiable on the entire domain or the entire interval. And that would be like from x equals a certain value to another value. Right? If the domain is restricted, so that means if there is a gap like this, where something either jumps, or if it's restricted as far as a vertical asymptote, okay, then it is not differentiable there at those restrictions. So here, the domain for this function right here is x is greater than or equal to negative 2. If x is less than negative 2, it doesn't make sense. It's not defined, so there's no derivative. We then move to graphing a derivative. So if this is your original function f of x right here, what we did was we took a look at derivatives at different points on the graph, and we simply graphed them on another graph that was straight below. So the derivative here, or the slope of the tangent, is 0. Therefore, this point on the derivative graph is 0. This point right here, derivative 0, so we place a 0 there. This would be about negative 1, so that's why we went down to about negative 1 or negative 2, whatever. And that's how you put together the graph of the derivative. Okay? In Chapter 2, just to answer that question, in Chapter 2, this actually is finding the derivative directly from first principles, or other wording is directly from the direct definition of the derivative. So in Chapter 2 we did this, so this may be on the exam. Okay, so we did this derivative activity, if you recall, and what we did is I wrote down a whole bunch of functions, and each of you took turns finding the derivative directly from the definition using the limit. And we noticed some patterns, right? We noticed some patterns. And from those patterns, you guys were able to come up with a few of the rules. And you guys came up with 2 or 3 of them, I think, right away. And that is this. The derivative of a constant is 0. That's the constant rule. The derivative of a constant is 0. You also noticed when we looked at the derivative of a function that if we have separate functions, like in this case, let's say function f, g, and h, and they're all added together, the derivative of this polynomial, basically, is the sum of all of the derivatives of each individual function. And that is true. Every term, you just simply take the derivative of this term and you write it down. Take the derivative of this next term, write it down. Take the derivative of this next term, write it down. Keep the same sign, whether it's adding or whether it's subtracting, like over here, and that's your derivative. So that's the sum difference rule. The other rule that you guys came up with is the power rule. This is the first major shortcut here for finding derivative. If you have a monomial like this, 3x squared, the power rule states that you take the exponent of the power, if it's a power like this, the exponent, you bring it down and you multiply it by the coefficient that already exists, and that gives us the 6 here. And then you subtract 1 from the exponent that we used, and that's the 1 here, and that's why this is 6x. So here's the formula for the power rule, and whatever the exponent is, you bring it down front, and that is the new coefficient. You subtract 1, done. If there's a number in front already, like you brought up, another constant like c, then this would be like n times c times x to the negative 1. Same thing. Okay? Alright, so we found the derivatives using those 3 rules. We did lots of practice with that, and you guys just did splendidly. Now, this one here, let's see. I'm not sure what this example was, but if we have negatives as exponents, you can just use the general power rule. All the rules hold with negative exponents, positive, negative, whatever. Okay? We also went over the fact that negative exponents in your answer can be written as positive exponents if you drop them to the denominator. So that's, to simplify, you're going to need to write positive exponents and factored wherever possible. In section 2.4, which is next, we talked about the product rule. Now, if you have a product of 2 functions, f and g, so a product of any 2 functions or terms or whatever, you can even have one single term that's written as a product, right? These are the 2 things right here. Then the product rule states that you define the derivative of this, you take the derivative of the first function, multiply it by the second function. You add to that the first function, the original function, times the derivative of the second function. And that together gives you the derivative. We did some examples right here where we split 12x squared into 2 different factors and we used the product rule. And we got the same derivative both times. So you could just take a look at that. And of course what that translates into is, you know, multiplying 2 binomials. If you want to take the derivative of this without expanding, excuse me, you can use the product rule. So remember, the product rule is the derivative of the first times the second plus the first times the derivative of the second, and here it is again right there. We also talked about, I guess we went over one of these questions from 2.3, and we showed you on the graphing calculator here that in order to find tangent slopes, or slopes of tangent lines, we need to find the derivative. And this question, number 10 on 2.3, was a little bit challenging in that we had to find the equations of the lines that were both tangent to the parabola and traveled through one of the points. And so you have to look back to your notes. Maybe you did this one and study up on this one, but you have to bring all the things together, find the derivative, let that slope be involve the point 2 and 1 in the slope, and yeah, then put it all together to find the equations of both lines. So you'll have 2 different slopes, and you can create 2 different lines using the 1 point. 2.5 was the quotient rule. Similar to the product rule, there's a special arrangement for finding the derivative of the quotient of 2 separate functions. And so if you have a function like this on top, x plus 1, and it's divided by another function, let's say like this, 6x squared, then here is f and here is g, and you follow this pattern right here, the quotient rule. We did some examples doing the product rule for the same function and doing the quotient rule for the same function to see if we get the same answer. But anyways, quotient rule, just to memorize that right there. And of course, make sure you've done your homework and lots of practice. These questions can get a little bit long, but you know, if you make sure you're as careful as possible. And remember that some of the questions on the test will say, do not simplify, which means that, hey, if you're going to do an example like this right here, if this is the question, This is your answer right here. Done. That's all you need to do. Just one step. Show me the rule. Show me the expression for the, and you don't have to simplify. So some questions you get to stop here. Other questions you're going to have to go down, to here. All right. So that was 2.5. Now 2.6 was something called the chain rule. Okay. The chain rule talks about a function inside a function. So we have these pictures of these onions. A function within a function, we have to differentiate twice. And we differentiate the outside function, we multiply it by the derivative of the inside function. And we keep doing that over and over until we've basically touched every part of the function. So I highlighted the outside function here in this example. That's something to the power of 7. That's the first outside function. The inside function would be then 5 minus 3x. That's the inside. And so here's an example of chain rule. And again, this is Leibniz notation here. The outside function would be the f function. The inside is the g. And so you take the f prime, or the derivative of the f function, leaving g alone, right? Don't touch g. Don't change it. Then you multiply by the derivative of that inside function. So here is the format of the chain rule. We also talked about what you might do if you have 3 functions, right? And you just do the same thing. You take the derivative of the outside one, leaving everything alone. Derivative of the next one, leaving everything alone in the inside. And finally, the derivative of the innermost function, then you're done. What the Leibniz notation for the chain rule was, that was an interesting lesson when we talked about FU. But U is representation for another function, right? And so if you take the derivative of the outside function, multiply by the derivative of the inside function. The Leibniz notation looks like this. Derivative of the outside function with respect to the inside function. And then times the derivative of the inside function finally with respect to x. Which simplifies, to your, okay, I'm not erasing that very well. So you finally get the Leibniz notation, which is the derivative of the y function with respect to x variable. So it's like, y equals 2x plus 1. That's the same. This is the same as saying y prime. Y prime means with respect to x, right? F prime of x. Or it also means dy dx. So yeah, so d over dx, if you're asking about that, you have to have some kind of function listed here. This doesn't occur on its own. This would be the y then. So next thing we talked about in 2.7 was implicit differentiation. Explicit functions are one variable in terms of the second variable, done. Implicit is an equation where the variables are kind of mixed up in the entire equation, both on the same side, left and right, and blah, blah, blah. So we can differentiate explicitly using the rules that we've talked about, but also we can use those rules to differentiate implicitly. And so I often like to refer to x, if it's a function of x like this, I like to refer to x as the preferred variable. So even when it's not a function of x and it's like x squared plus 2xy, minus 5y squared equals 7, y and x are all mixed up in there. But x is our preferred variable. And so the reason why I say that is because we know that the derivative of x is 1. The derivative of y is not 1. Even though it's a variable, it's not the preferred variable right here. So when we do that, we use things like the product rule, and we remember that in this case, 4xy, we remember that 4x would be a term that contains the preferred variable, and then y is the non-preferred variable. So we would want to split it up like this, and then use the product rule. Implicit differentiation, basically, you don't have to write y all by itself on one side in terms of only x, because those functions can get really complicated really fast, and the differentiation is super tough. But if you just leave everything all jumbled up, you can use some of these same rules and get it done. So here's another example right here in black. You know what? X to the fourth. That's just an x term, so you just do your power rule. Y to the fourth, though, this is like an alien variable, right? So you got to do the chain rule. So 4y cubed times y prime, chain rule. See that? Derivative 17, 0. Isolate for y prime, and you've got it. Usually, in these cases, the y prime will be explained in terms of both x and y. All right, that was 2.7. Yeah, that's implicit. Then we talked about higher derivatives, right? That was 2.8, and I'm just going to skip down here. Higher derivatives, 2.8. Higher derivatives like y double prime, y triple prime, okay? And the easy thing about this is to find y double prime, you simply take the derivative twice. It's just exactly like you would think it should be. You take the derivative of the function, then you take the derivative of the derivative. It's super easy. Look at this super easy example right here. We have a function right here, y equals x to the fourth plus 6x squared. You take the derivative to get 4x cubed plus 12x. Then you take the derivative again of this one, and you've got your second derivative. You can just keep going. Derivative again, you get the third derivative. You can take the derivative of this to get the fourth derivative, and so on. Eventually, you'll probably get down to fifth, sixth, seventh derivative, whatever. You eventually get to 0, okay, for most things, especially if it's a polynomial. But really easy, and yeah, this brings us to, there are a couple tricky questions in that that I don't think we quite went over. But anyways, for those of you that are watching this video, your test may be just exclusively Chapter 2. It may include 3.1 and 3.2 as well, which most of these tests will. So I'll just quickly go over 3.1 and 3.2, the applications. In this section, what we talked about was the fact that the first derivative is actually representative of velocity for a position-time graph. That's something we've talked about before. That's not earth-shattering. It's not brand new. But we explain why that is. We also looked at the graph of velocity versus time right here, and we found out that the instantaneous rate of change of velocity over time is actually something called acceleration. So we introduced the fact that the rate of change of velocity over time, that is meters per second, comes out to meters per second squared. That's acceleration. So the change in velocity, if your velocity is ever increasing over a specific time interval, that means you are accelerating. So we just introduced that notation and that language. So here you go. This is kind of the important part of that lesson. For a position-time graph, the first derivative is velocity. The second derivative is the expression, at least, for acceleration.